Welcome back to the third week of getting started with competitive programming. I hope that you're excited about exploring a new theme, and in this week our focus will be completely on greedy algorithms. So greedy is a fairly broad algorithms design paradigm or technique, and it's fairly popular in contest programming. And in our first module, we are going to be illustrating the technique through a problem called pancake flipping, which is from the Google Code Jam Qualifiers back in 2017. Before we get started though, let me just say a couple of things about greedy algorithms in general. In most algorithms textbooks, you will find a lot of warnings about greedy algorithms. For instance, here is the table of contents from Jeff Erickson's algorithms, which by the way is an excellent reference that goes along very well with this course, incidentally. And the warning here is fairly explicit. It says greedy algorithms never work. Well, this is a bit extreme. They, of course, do sometimes work, but the thing to be careful about is that they often don't work, despite being very natural sounding and being the most tempting first cut approach to a problem. So for most optimization problems, you will probably naturally come up with a greedy style or a greedy approach to it, which by the way is essentially characterized by doing whatever you need to do with minimal effort, whatever seems like the right thing to do in the moment. I really don't know of a formal definition of what makes an algorithm greedy, although there are some really interesting mathematical formalisms around characterizing when a greedy algorithm will actually work. And if you're really interested in this, then the thing to look up is matroid structures, but you can completely ignore this comment for now. If you're curious, there are of course more links in the description as usual for you to pursue further. But in any case, as I said, at a high level, a greedy strategy is something that feels like the right thing to do locally, but it turns out that long term this could have ramifications that make your solution suboptimal. And that's what happens most of the time, and that's why you need more sophisticated techniques like backtracking or dynamic programming or divide and conquer or whatever else that helps you cut through the search space in a more meaningful way. But it turns out that for many problems, even classic ones, greedy algorithms sometimes do get lucky and happen to work out all the way. Our goal with the lectures this week is to develop enough of a feel for why greedy algorithms do work when they do, by giving you enough reasonably formal justification for the correctness of the approaches that we do discuss. On the other hand, we will also try to go over examples of when greedy algorithms don't work, so that you also develop the practice of looking for counterexamples to see that these strategies that you come up with might fail. However, during a contest, you might just find it easier to code up your greedy algorithm and see if it actually passes the tests or not. And this would be a reasonable thing to do, especially if you don't have penalties for wrong submissions. It may just be the faster approach because greedy algorithms typically tend to be simple and so not so difficult to code up. So you could do that quickly as a preliminary test if you have an approach for which you cannot quickly come up with a counterexample and it seems like it might be promising. However, outside of a contest environment, it's definitely a good idea to actually go through the process of trying to understand why your greedy algorithm works or why it doesn't work. Now, this is also a good time for me to point out that greedy, being a fairly universal idea, will keep coming up in future weeks as well. So watch out for the reappearance of greedy-based ideas in various other contexts as we go along. So with all that background in place, let's finally talk about pancake flipping. Now, normally I start off with a problem statement, but here I'm going to start off with a bit of logistics. I'm going to replace the concept of a pancake with a cookie in the entire story, just because it was easier for me to find pictures of cookies. So sorry about that, but I promise you that nothing changes in terms of the mechanics of the problem statement or the solution for that matter. So first, let's talk about the two faces of a cookie. So you distinguish between the top side and the bottom side of a cookie. So the top is going to look like this throughout the slides, and the bottom is going to look like that. So according to the terminology in the problem statement, these are called the happy and the blank sides respectively. So the top side has the chocolate chips, and it's the happy face, and the back has nothing, and it's the blank side. Now what's going on is that these cookies are being baked on a single row. It's some sort of a long oven thing, and the cookies are just being processed in some left to right order, and as you can see, some of them are face up and some of them are face down. Now our task is to make sure that all of these cookies are face up, and we need to flip the ones that are face down for this to happen. Now what we have at our disposal is not something that can flip a single cookie at a time, and the oven is too hot for you to do that directly, so you have to use a flipper. But unfortunately the only thing you have been given is an oversized cookie flipper. So it's something that can flip cookies in batches. So here is an example of an oversized cookie flipper of size 3. So it can flip any 3 consecutive cookies at once, and notice that it flips them one by one. So it doesn't change the ordering of the cookies. So the cookies stay in place. So you can imagine just scooping up the cookies from the front and just turning them over. So the left to right order is not affected, but the state of all the individual cookies basically flips and gets reversed. So let's do another example. Suppose we move the flipper over here and flip again. Then notice that we go from being face down, face up, to being face up, face down, face down. So as usual, our first question would be, can we always manage what we have set out to do? So we have a row of cookies, some of which are face up and some of which are face down. We also have at our disposal this K cookie flipper. So K is the number of consecutive cookies that can be flipped in one shot. Once again, remember that the cookies stay in place. The left to right order is not reversed. It's only the individual states that are flipped, and they are guaranteed to be flipped. So there is no, it doesn't depend on the skill of the person that's using the flipper. The cookies definitely get flipped. They don't drop anywhere, they don't get lost, etc., etc. So that's hopefully the mechanics of the problem are hopefully clear at this point. And the question I'm asking is, can we always do this? And I have for your reference the limits that are given in the problem statement. So let's just go over a little bit of notation. So the initial state of all the cookies is given by a string S, and the encoding is that it's a plus if it's initially face up, and it's a minus if it's initially face down. Remember, face up is what we call the happy side, and face down is the blank side. And what you want to know is if you can use a K-sized cookie flipper to fix up all of them, which is to say make everybody face up at the end of the day. So again, take a pause here and think about whether you can come up with scenarios where this task is impossible, or can you come up with an argument for why, even if it takes some time and it's a tedious process possibly, but you will still always be able to manage. Okay, so hopefully you had a chance to think about this, and notice that there's something interesting going on with the limits for K. So we see that K is at least 2, and notice that if K was in fact 1, which is that you have a flipper which is like an ordinary cookie flipper. It's not an oversized flipper. It lets you flip one cookie at a time. Then of course you can always fix any sequence of cookies by just going to the ones that are facing the wrong way and flipping them over. So this is probably not such an exciting question anymore, and perhaps that's why the range of K is between 2 and something. It's truly an oversized flipper. And notice that when k is equal to 2 already, it's not very hard to come up with an example where it's impossible to achieve this task. And again, this is a bit of a spoiler alert. If you didn't have a chance to pause before, maybe you want to think about this now with this hint in place. Alright, so notice that even with k equals 2, which is the most basic kind of an oversized flipper that you could be working with, you could get stuck with just 2 cookies in front of you. So if one of them is facing the right way and the other is facing the opposite way, then no matter how many times you try to flip them over, you'll just get them to being in the opposite situation, but it'll never really get fixed. Notice that you cannot flip something at the edge of the oven. So in particular, I think we will have some visuals that make this clearer later. But essentially, once you have reached the last k cookies on this row, you cannot flip anything that is after that, because your pancake flipper just does not have enough place to fit in. So you can imagine that it's not an open space where it can, hang over the edge. You really get stuck at the very end. So for instance, just to make this specific, if you are here, then you might think, let's flip once to fix the state of the first cookie. And now from here, let's try to just flip the second cookie onwards. And what I was saying is that that is not allowed in the definition of this problem. There is no onwards from the second cookie if you have a pancake flipper of size 2 or even more. So this is not going to work. You will have to flip both of the cookies that you have in front of you in sync, and that is why this situation can never be fixed. So there are clearly situations that are impossible, and our task at a high level boils down to being able to identify these and distinguishing it from those cases where there is a feasible strategy for flipping everything over. And in that case, our task is also to additionally find the minimum number of flips that we need to make everything work. Okay, so before we start thinking about an algorithmic strategy, let's just continue making some preliminary observations. So here is a first question that I would like to pose to you. Do you think the order in which we make these flips matter? So suppose somebody comes up to you and says, okay, look, here's what we can do for this example. We could flip from the first location, then we could flip at the second location, and then we could flip at the 7th location. So you could try executing these flips and see what happens. But then somebody else comes along and says, no, let's flip at the 7th location first, and then go back and flip at the second location, and then flip at the first location. So what do you think the outcomes will be for these two different ways of doing it? Will the final state be the same, or will it be different? If you can think of some other ordering of these 3 flips, then try that as well and see if you get to a different final configuration. More generally, if you have a set of flips where each flip can be uniquely pinned down by identifying the position at which the flip begins, and once again remember that your legitimate starting positions are between the first position and the cookie that is at the n minus k plus 1th location. So any location in this range is a valid location for you to start off a flip. And now from here, what we really want to think about is whether the sequence in which we perform these flips matters or not. So what you want to do is either come up with an example of a set of flips that can be played out in 2 different sequences and they lead you to 2 different final outcomes, or you want an argument which says that no matter which sequence you pursue these flips in, the final outcome will always be the same. So which one is it? Give it a thought and come back when you're ready. Okay, so hopefully you had a chance to think about this. As usual, let's try to work through this in the context of a specific example. And let's say that we want to perform the flips that you can see come up on your screen. And by default, let's say that we just perform them in the order of appearance from top to bottom. Now, let's also try to live this experience through the lens of a specific cookie. So let's just focus our attention on the 6th cookie that's on the table right now, just as an example, and let's try to focus on the experiences that it goes through as you perform these flips. The first flip does affect the cookie, so it's going to get flipped. Its state is going to change. The second and the third flips don't influence the state of this cookie. In fact, even the fourth one does not touch this cookie at all, misses it by a whisker. So right now, the state of the cookie is just that it was flipped once from the beginning of the process. Now, the next flip is going to flip this cookie over again, and so is the next one. So in all, this cookie has been flipped 3 times. Notice that the last flip again does not affect the state of this cookie. So overall, at the end of the day, this particular cookie was flipped 3 times, and that's going to be true no matter what order you perform the flips in. So hopefully that's clear. And notice also that there was nothing special about the 6th cookie in this list. Whatever we said is true for every single one of them. Therefore, no matter what the order is in which you perform a set of flips, the final outcome is going to be the same. So the order does not matter. An easy consequence of this observation is the fact that you never need to repeat a flip, because if you have a sequence of flips that does something and there are redundant flips, or let's just say repeated flips, they're not redundant yet. So what you could do is reorder the flips so that all the repeated ones come one after the other. And now notice that all these repeated flips are not really doing any valuable work for you. The only thing that matters is the parity of the number of times you repeated them. So if there is a flip that you perform, say 6 times, then that's as good as not performing the flip at all. That'll be the same thing. If there is a flip that you perform 7 times, then that's equivalent to performing it just once. So why would you perform all of these extra flips? Remember that we are trying to minimize the total number of flips that get us to the answer. So we know that without loss of generality, we can assume that flips are never repeated. Now let's go back to something that we have said before, which is the total number of possible flips that can happen in the first place. So notice that the legitimate locations where you can start a flip are the locations including the leftmost location on the table and all the way up to the n minus k plus 1th location. At the very end, as we said, there isn't enough room and further flips are not possible anymore. So really you have these n minus k plus 1 possible flips, and at this point you might be tempted to think about a brute force approach to solving the problem. So given that there are only so many flips you can make, and given the fact that the order doesn't matter, the question really just boils down to which flips are you going to make, because we also know that flips are never repeated. So what is the complexity of a brute force approach based on all the observations that we have made so far? Think about that for a minute and come back when you're ready. All right, so the dominant term in the complexity of the brute force approach is going to be 2 to the n minus k plus 1. So it turns out that you could just try all possible subsets of locations where you want to actually flip. If you try all of them and then simulate the flips and basically check if everything works out, then essentially you're going to be trying all possible subsets of a set of size n minus k plus 1, and that's going to be the complexity. There's going to be a bit of a polynomial overhead, but I've not written that down because this is really going to be, as I said, the dominant term. But if you wanted to do it properly, the running time analysis, then you should also account for the amount of time it takes for you to actually simulate the flips and check if things work or not. Now, even without these observations, you could just try to brute force your way through the space of all possible flips using something like a BFS over this space. You could say that 2 states are adjacent if they are reachable one from the other via a single flip at some location. And I'm not going to elaborate too much on this strategy, but essentially there are other approaches in the spirit of brute force that would also work if you were working with a small data set on this problem. However, that's not going to scale when you're working with a large data set, so we need to think about this some more. And this is where the greedy ploy comes into play. So let's think about what is the absolute minimum work that we need to do at every stage. So starting from left to right, let's begin by focusing on the very first cookie that we encounter, which is facing the wrong way. So this right here is the leftmost cookie that has a blank side up, and notice that any valid solution will have to flip this cookie. Now in our solution, what we are going to do is position our first flip to start at this location. Notice that all the cookies that have appeared before this are facing the right way just by definition, and it seems wasteful to start a flip anywhere earlier because it seems to be just unsettling things that are already fixed. So as they say, let's not fix what's not broken, and position our first flip at the location of the leftmost cookie that is facing the wrong way. So we start there, then we execute the flips. In the program, you could basically simulate these flips, and then you move the flipper along to the very next cookie that is facing the wrong way. So you just walk along and stop when you see another cookie that's facing the wrong way, and you position your next flip there, and you keep doing this till you reach the very end. Now, I'm not actually executing these flips for you, and I'll leave this as an example that you can work out. Feel free to pause the video here and sort of go through the process. And now let's think about when we would declare an actual answer versus when would we say that the initial configuration is impossible with the value of k that we have been given to work with. So when we finish, when we stop and get stuck, notice that we have actually fixed the states of the first n minus k plus 1 cookies just by the way that we have been performing these flips. So that's easy to check. The only thing that remains to check is the state of the last k minus 1 cookies. If these last k minus 1 cookies are not already facing the right way, there is nothing that we can do to fix them anymore. So at this stage, we will declare that the situation is impossible, but if the last k minus 1 cookies are facing the right way, then we will say that we are done, and then we will report the number of flips that we have made. Notice that when your algorithm actually outputs a number, it's definitely doing the right thing, because we have seen that we only made those flips that we were absolutely compelled to do. So we know that any solution, and in particular the optimal solution, also must make at least that many flips. And because we have actually demonstrably managed with that many flips, because notice that by construction, when we are done and we actually output a number, we have also given you a strategy for making a sequence of flips which will actually fix everything, and that is visible. So whenever we output a number, we know that we are at par with optimal and we are doing the right thing. The only thing to be careful about is when we report impossible, then we need to be sure that there is no other solution that actually manages to flip everything to its correct position, while we just maybe missed out on it because of our greedy choices. Now, you can actually argue that this algorithm does the right thing even when it reports impossible, and I will leave that as a little exercise for you to figure out in terms of what is the logic for why our impossible output is also always correct. Now, if you're stuck on this, then you can go back and look at the notes on the course website, and you will find a more elaborate argument there. Now, in terms of implementation, you could exactly implement what we have discussed so far, and that will work. It'll have a complexity of something like order n squared or n times k, because you're doing sort of a linear pass, but within each pass you're trying to figure out if a flip needs to happen or not, and if it does need to happen, you do have to simulate the flip. So that's going to be k units of work in every iteration. Now, this is good enough to pass the large data set. So once again, please feel free to give it a shot and let me know how it goes. In the meantime, let's now discuss a small improvement to the implementation that we have just described. What we will do is trade off some space for time, which is to say that by keeping track of a little more information, what we will be able to do is bypass the simulation, which forces us to do order k extra work in all those iterations where we do decide to make a flip. As a result, what will happen is that we will end up with a purely linear time algorithm, one that runs in order n, but it uses order n extra memory to do this additional bookkeeping. Now, this is an optimization that has also been described in the official editorial, and as is pointed out there, you don't actually need this improvement for the large tests to go through, Nonetheless, it's a useful trick to be aware of. So that's what we are going to try and understand now. And this is also the version that we will implement. However, if you do have an implementation of the simulation-based approach and you want to share it with us, then please feel free to initiate a pull request in the GitHub repository where we are maintaining the codes for these lectures. All right, so let's go back to the original state of the array. And once again, let's begin with the leftmost cookie that needs a bit of a nudge. So our overall strategy will still be to have this for loop that is running through the initial state array. And the way we will deal with what we decide to do when we have to make a flip will be slightly different from before. So here is the first location where we do need to make a flip. So the natural thing, of course, is to track this in a flip or an answer variable to remember that a flip had to be made. And now in the simulation approach, what you would have done is you would have either flipped the state of the next k-1 cookies as well by actually changing the state array, or you would have tried to keep track of this information in some other auxiliary array by recording a number of flips at every location and incrementing them as appropriate. But notice that we really want to avoid having to do something k times or k-1 times or whatever. Think about what is it that we really need to know when we are processing the cookie at the jth location for some j. What we really need to know is how many times has this cookie been flipped so far. And a hint to that is in the flip variable. So the flip variable tells us how many flips have happened so far. But that may not be the number of times that this cookie has been flipped, because many of these flips have happened far away and are not relevant for this cookie. So what we really need to know is how many of these flips are obsolete for the current variable. I shouldn't say the current variable, but rather the current cookie, the one that is being processed right now. So what we do is we keep an extra array called the obsolete flips array. And there what we do is we make a note of the fact that this flip, the one that's the leftmost flip on your screen right now, is one that should not be counted when you're processing the k+1th cookie away from the current location. So it becomes an obsolete flip for that cookie. So when you're processing that cookie in the future, when you look at the number of flips that have happened, you're going to also subtract whatever is being stored in the obsolete flips array at that point to get the accurate number of flips that actually affect this cookie. Of course, you might say, look, this flip is obsolete not only for the k+1th cookie from the current location, but for all the ones after that as well. So why don't we increment the values in obsolete flips, that array, for all of the future locations as well? Well, we could do that, but that would defeat the purpose of getting to something faster, right? Because then that would mean actually doing n-k amount of work in the worst case. So we don't want to do that. Instead, what we will do is we will just do some sort of a running sum of the number of obsolete flips. So in particular, when I land at the jth cookie, I just look at the obsolete flips value of the j-1th cookie. So the number of flips that have been obsolete for the previous cookie, they're all certainly obsolete for me as well, because if those flips couldn't reach the cookie to the left of me, then they can certainly not reach the cookie at this location j. So we borrow that value from the previous value stored in the obsolete flips array, and then of course we also look up whatever was hinted to us from the flip that happened from this action that we're doing right now. So that gives us the total number of obsolete flips, which we subtract from the actual number of flips to recover the correct number of flips that this cookie was actually involved in. Now this may be a little bit tricky to fully understand, so feel free to pause and take a moment here to really absorb this. Hopefully it'll also become clear as we go into the implementation. Before we can get to the implementation though, there is still one piece left that we need to understand. So once we are processing the jth cookie, we need a way to figure out if it needs to be flipped or not. When we were doing simulations, this was really easy because you just looked at the state of the cookie because it has actually gone through all the flips that have happened so far. The state of the cookie is reflective of its current state. So we know that if it's facing the correct way, we can skip it, and if it's blank side up, then we need to flip it. But now what you have is the original state of the cookie from the state array, and you have this number, which is the number of flips that it has experienced so far, which once again you obtain by subtracting from the flips variable the obsolete flips value. Now, based on these two pieces of information, which is the original state of the cookie and the number of flips that it has experienced, can you come up with a criteria for when you should actually flip this cookie? So take a moment here to think about this, because once you have come up with this criteria, you would have a complete description of the algorithm that you need to implement. So you just go through the whole set of cookies from the first position to the n-k+1th position, do the flips that are necessary, and then you essentially continue doing this for the last k-1 cookies as well. But this time, if your criteria does trigger and it says, look, you have a cookie that needs to be flipped, then instead of incrementing the flips variable and proceeding, what you will do is you will break out of the loop and declare that the situation is impossible. If, however, your loop survives for the last k-1 cookies as well, then you can just report the number that you have in the flips variable. So that's your entire algorithm. The only piece that you need to fill in is what is the criteria for determining if the cookie that is being processed currently needs to be flipped or not. Once again, to recap, you have the value of the original state of the cookie and the number of flips that it has experienced so far. What would you do from here? Okay, so hopefully you had a chance to think about this. The criteria is actually fairly natural. If the cookie was plain side up in the original array and the number of flips that it has experienced is even, that means all these flips have cancelled out, then even at this stage, the cookie is still the wrong way up. So you do need to flip it. On the other hand, suppose the cookie was facing the right way to begin with, but now it's experienced an odd number of flips, then you are in trouble because you have actually broken something that was correct in the beginning. So now you need to flip it again to fix the situation and bring it back to the happy state. So that's your criteria for determining whether the current cookie needs to be flipped or not. And as we were just describing before, with this piece of the puzzle in place, you now have the entire algorithm in your head, hopefully at this point. And once again, if you want to give this a shot, this would be a good time to pause this video and try out the implementation yourself. The implementation that we have for you in the video is going to be in Python, but really we only use very simple data structures, and it should be completely straightforward to translate this into a language of your choice. So to begin with, as usual, we just read all the input. T is the number of test cases, and every line is one test case. The first string is going to be it's going to be a sequence of characters with no spaces, which essentially is composed of pluses and minuses, reflecting the original state of the cookies. And then there's a space and there is a number, and that number is k. So that's essentially what we are reading in two variables named s and k. So s is going to be a string and k is going to be a number. Then, let's just use n to record the length of the string, because that's going to come in useful for stopping criteria for our main for loop. So we have n being the length of the string or the number of cookies to begin with. Now, we also have this obsolete flips array that we just described. To begin with, everything in this array is 0. There are no obsolete flips to record before the process has even started. We also declare an answer variable. In the description in the video previously, we called this the flips variable, but yeah, you could of course call it whatever you like. In this code, this is the answer variable, which has been initialized to 0. Okay, so now let's do our first for loop, which goes from the start of the array all the way up to the n minus k plus 1th cookie. Now notice that because we have 0 indexing, you really need to go only up to the n minus kth cookie. And the way range works in Python, it doesn't actually go to the last number is omitted. So that's why we have j in range 0 to n minus k plus 1. This does the right thing, okay? All right, so the initial state of the cookie can be read off from s of j. So we do that and we store that in state. And the first thing we do, of course, is borrow the obsolete flips from the previous obsolete flips value. So notice that you might get an out of range error when j is 0 because what is j minus 1? This being Python, this is just going to read off the last element in the array. This is an initial condition thing. You could think of it as an edge case. I haven't really bothered to say j greater than 0 because there's no harm to begin with. Every value is 0, and what happens in the first iteration really doesn't do any harm here. In a different language, you may have to be more careful about what happens at the first index. But in general, what you're doing is you're borrowing the number of obsolete flips from your neighbor, because you know all of those flips are obsolete for you as well. And of course, your current value needs to remain. Anything that has been explicitly pointed out, you need to retain that value as well. That is why this is a plus equals. You're not copying the value over. You are using that value to increment whatever value you had in the first place. So this correctly records the number of flips that should not be counted for the jth cookie or pancake or whatever. And now the next thing that we want to do is, actually record the number of flips that are relevant. So that is going to be the total number of flips that have happened so far, which has been stored in the answer variable. And you subtract from this the number of obsolete flips. So that should be fairly straightforward. And this is the number of actual flips that we need to consider. Now, if you remember from a few minutes ago, we had come up with this criteria for whether the current cookie under consideration should be flipped or not. And what we said was that it should be flipped exactly when either the original state was plain or minus and the number of flips is even, or when the original state was happy but the number of flips was odd. So let's just record these in two Boolean variables. Of course, if you're writing this code during a contest, you will probably not really do this. You will most likely write an if condition straight out, but I think this is easier to read, and since we have all the time right now, we have these descriptive variables here. So original destroyed is true if the original state of the cookie was a plus or a happy state, and the number of flips is odd, which is to say that you actually destroyed what was correct to begin with. The other variable is blank not fixed, which is to say that the original state of the cookie was that it was plain side up and the number of flips is even, so we still have work to do here. So if either of these variables happen to be true, then we should actually go ahead and make a flip. So the way we record that, of course, is to increment the answer by 1 to say that one more flip has been made. And more importantly, or equally importantly, we need to go to the obsolete flips array and make a record there. So look at the cookie that is k steps away from the current one, and actually k plus 1 steps depending on how you're counting. And basically this is the earliest cookie, the cookie with the smallest index that is not affected by this flip, and we do need to make a note of that. So that's what we are doing here. So the obsolete flips variable needs to be appropriately incremented. As I said, you could also just increment all the values for obsolete flips for all larger indices, but that would be very expensive to do, so we're not doing that, and instead we do the trick of borrowing a previous value as we did at the start of this for loop. Okay, so that's essentially the first part. The second part is to go over the remaining k minus 1 cookie. So we run the exact same loop, right? We do the exact same thing. The only difference is that this time, if you realize that a flip needs to happen, then you don't have the facility to actually make it happen. So at this point, you have realized that you have an impossible task upon yourself. So you declare the answer to be impossible and you break out of the loop. Now, if you do survive the loop, of course, then the answer variable does have the right number. So you can just go ahead and directly print the answer. There is a string conversion here because Python will probably not print the integer directly, but the string conversion will not hurt if answer was reset to a string. And again, I think with if you have a language where you have to worry about types, you may be a little bit careful about how you do this. You may need to store an extra flag variable or something like that to detect if you went into that breakpoint in the second for loop. But whatever you have to do is going to be completely straightforward, so I'm sure it's not going to be a problem. So with that, we actually come to the end of pancake flipping, and I hope that whatever we discussed made sense. At any rate, the more basic version of the algorithm without this optimization should be extremely doable, where you just go over the state array and simulate all the flips that need to happen, just check if the last k-1 pancakes got automatically fixed or not. But hopefully the optimization also made sense. And the one thing that I'll leave you with as food for thought is something I've mentioned earlier about trying to convince yourself that whenever the algorithm says impossible, it didn't miss some way of doing things correctly. We have already argued that if you output a number, then that's going to be the right number. You just need to make sure that your impossible outputs are also accurate. It turns out, of course, that they are, but you need to convince yourself using some sort of a logical argument. So with that, we come to an end of this video, and next time we will talk about another fun problem called Islands War. So I'll see you there, and thanks so much for watching as always. Bye for now.